Okay. All right. So today we'll talk about the problems from the assignment. Right. So here are the problems. So let's get started quickly. So the first problem I think we've done in class about the determinant. Do you want me to do this?
Sir, I think a question similar to that was asked in the midterms too.
I don't.
Sir,
Well,
it
that
has been done in your notes, so you can
it's not
skip
in
it.
my notes. I can skip
Hmm.
it, right? You're okay with
Ah,
this?
yeah. Whatever you have done in the notes, you can skip it.
Okay, fine. So you know how to do this, right? Yeah.
Yeah.
So okay, I'll tell you what the answers are, but you should know how to derive them, right? So the derivative at the identity acting on a matrix H is the trace of H, right? And the derivative at some A acting on H, what will this be? Well, f of A plus H is what? It is determinant of A plus H. So that is, you take the A common and this becomes determinant A into determinant of identity plus A inverse H. And so this becomes using the fact that the derivative of f at the identity is the trace, this becomes determinant A into 1 plus trace of A inverse H plus big O of norm H squared, or little o of norm H if you like. And you multiply out, you get determinant A plus determinant A into trace of A inverse H. So this becomes determinant A into trace of A inverse H. Okay, fine. So the second problem is you have a map from matrices, n by n matrices, to symmetric n by n matrices. F of A is A transpose A. So we have to work out the derivative, right? So we look at f of A plus H, right? So this is A plus H transpose into A plus H. So you expand this out. This is A transpose A plus, so the next term will be linear in H. So it will be A transpose H plus H transpose A. And then you have a last nonlinear term in H, which is H transpose H. So this is of the form f of A plus some linear map depending on A acting on H, right? This is linear function of H. And then you have an error term, right? And you have to show the error term is little o of norm H. Then this linear term will be the derivative, right? So what is the norm of the error term? This is the norm of H transpose H. And we know the operator norm is, it satisfies a multiplicative inequality. This is less than the operator norm of H transpose into the operator norm of H, right? And what is the operator norm of H transpose?
Same as operator norm of H.
It's the same as the operator norm of H. Okay, so this is little o of norm H. So one question, why is the operator norm of H transpose equal to the operator norm of H?
You can do it using inner product and
Correct,
the
yeah, so
operator norm of H transpose.
yes, that's right, yeah.
The
So
operator norm of H transpose is supremum of all norm v equals to 1,
correct.
H transpose, inner product H transpose v, comma v.
So wait, let me write the definition, okay? The definition is, it is norm of H transpose V, right? This is the definition.
Yeah.
Okay, so now let me square both sides, then I can bring in inner products, right? So I square this, I square this. So then this becomes sup over norm V equal to 1 of inner product. So I get H transpose V, H transpose V. One of the H transpose I can take to the other side. This becomes H transpose VV, right?
Yeah.
Yes. And what is this? This is a quadratic form, right? Which is, I mean, the associated matrix is symmetric and positive semi-definite, right? So this is equal to, if this has eigenvalues lambda 1 to lambda n, then this is the maximum eigenvalue, right? So this is maximum eigenvalue of H transpose. Is this all right? Yeah. And norm H squared similarly is equal to the maximum eigenvalue of H transpose H. Is this all right?
Yes, sir.
So why are these two the same?
They are self-adjoint.
Yeah, they're self-adjoint. So I'm looking at two self-adjoint matrices, H transpose and H transpose H. I'm looking at the eigenvalues. So why is the largest eigenvalue the same for both of these two? Why is that so? Anyone? Why are these two the same?
Oh, sir, in the first line where you have computed norm of H transpose squared,
Yeah.
so there you can, I mean, lambda n is same as supremum of norm of v equals to 1, v comma H transpose H v, right? Because
No.
this is real.
No, look, this is inner product of H transpose V with H transpose V.
Mm-hmm.
So I can take this H transpose to the other side, it becomes an H.
Oh, okay, okay. Yeah.
Yeah. So I'll get H transpose VV. Yeah. And similarly, that's how I got the second one, right? For H squared, it will be the maximum value of H transpose, eigenvalue of H transpose H. Right. So yeah, why are these two the same? Anyone? Yes? Anyone?
Is there okay? Would it be because since it is a transpose H transpose and H would have the same, he would have the same eigenvalues?
Yeah. So why is that? Look, if H is invertible, then if I do H inverse H transpose H,
Hmm.
what does this give me? This gives me H transpose H, right?
Yes, sir.
So if H is invertible, the two matrices are conjugate. So they have the same
Hmm.
eigenvalues,
Hmm.
right?
Yes, sir.
So in general, what can you do?
Sir, in the general case, would working with the generalized inverse of H help?
Hmm.
Sir, I think this since this is finite dimension norm of H transpose V square, you can just break it using Parseval's identity and take H on the other side.
Oh, you want to write norm of H transpose V whole squared. This is sum over I
Yeah.
product H transpose V EI.
Square. Yes.
Oh, that's right. Yeah, that works. Thank you.
Yeah, in general, you can do it in separable case as
Sure. So this is V. Well, let's see if this works. I'm not sure. HEI squared. So then what do you do?
well. Oh, you can break
So
V,
now
right?
you choose, yeah, so H, well, H is not self-adjoint, so we can't do anything there. So what do you do here then?
You can break V, right?
Yeah, I can break, that won't help, right? Yeah, this is true, but does this help?
Like you can break V and add that cons. So suppose V is sum over Vj Ej, then Vj you can take it on the other side.
How can you take Vj on the other? You can take the Vj out. Yeah, it's a constant, scalars. Yeah. So does that help?
But The inner product is symmetric, right?
Okay.
No,
And
but H is not symmetric. H is not symmetric. Now, Orkojit, you
Okay.
have something to say?
so what I want to say is here, before I write this maximum eigenvalue of H times H transpose, I
Yeah.
apply Cauchy-Schwarz and just show that this H transpose squared, that thing is lesser equal to the norm of H transpose.
Yeah, that's correct. Fine.
That's correct.
That-
Now norm of H transpose is lesser equal to norm of H times norm of H transpose, right?
That's right. Oh, and then you cancel. Okay,
Yeah.
yeah. Okay, fine. You can do that. Yeah, fine. Yeah. Okay, so norm of H transpose. So what he's saying is norm of H transpose squared, this is less than or equal to the norm of H transpose, right? Because here you apply Cauchy-Schwarz, right? This is less than or equal to norm of H transpose V into norm V. So V has norm 1. So this will be less than norm of H transpose into norm V, which is 1. So this is less than norm H transpose. Now this, by the usual inequality, is less than norm H transpose. So if H is non-zero, then you get that norm H transpose. You just divide by 1 norm H transpose. This is less than or equal to norm H. And then you apply this again, and that implies that norm of H, which is norm of H transpose is less than or equal to norm H transpose. So therefore they're equal. Okay, yeah, good, that works. Yeah. Is this all right? So
Okay,
this
sir. Yeah.
for all H. And so norm H is equal. Yeah. Okay, this works. All right, fine. Okay, so I don't want to spend too much time on this. There's just a small detail. Look, if you don't actually need that norm H transpose is equal to norm H, you don't actually need that. You can just say that, look, norm H transpose by the equivalence of norms, right? This is less than a constant times the max over Ij of the mod of the ijth entry of H transpose, right? Yes? This is
Yes,
another
sir.
norm.
right.
Any two norms are equivalent, right?
Right.
And this norm, this is the same as the max over Ij of mod of H Ij, right?
Mm.
Because H transpose and H have the same entries, just permuted. And so this norm is again less than a constant times the operator norm of H. Okay, so you can at least say that norm H transpose is less than some constant times norm H. Okay? All right. Yeah, so what you need is basically here the operator norm is less than C times the L infinity norm. This is the L infinity norm on R power n squared and bigger than 1 over C times the L infinity norm. Okay? All right. Is this
Yes,
okay?
sir. Yes.
Yes,
Yes,
sir.
sir. Yes.
Okay, okay. So let's carry on. We don't want to waste too much time on these small details. But okay, so that gives, okay, so we've computed the derivative, right? The derivative will then be the linear term here. So the linear term is A transpose H plus H transpose A. Okay. So, okay. So df at A acting on H is A transpose H plus H transpose A. So now this is part A, and then part B is you have to show that if A is orthogonal, then this has full rank. Right. The reason for doing this is to show that the orthogonal group is a manifold, right? Okay.
Yes, yes, yes.
Using the rank theorem, right? You'll get that this is a manifold. If you can show it has full rank. Okay, so part B, you have to show that to
I
show
mean, it's showing the map is surjective, right?
correct,
Any
yeah.
C belongs.
We have MNR to SimNR. So is surjective is onto if A belongs to ONR. So how do you do this? So you're given, let's say B, which is a symmetric matrix. So how you want to find an H so that this A transpose H plus A transpose A is equal to B, right? So how do you do this?
Yeah, we will break B as half B plus half B transpose and then equate
Right.
A transpose H to B. The other
Okay.
part would be automatically equal.
Right, right. Okay. So fine, good. So put H, A transpose H equal to B. So half B,
Even
sorry,
half B, half B. Yeah.
half B. So H becomes half B, half A transpose inverse into B, right? And A transpose inverse, this is equal to A, right? Yes,
Yes, sir.
since A is in ON. And so then, as you're saying, H transpose A will be what? This will be half B transpose A transpose, but B is symmetric, so this is half. Sorry, sorry. There's an I missed out an A. Yeah. So this is H transpose is just this into A. So the A transpose A cancels because it's orthogonal. So this is half B transpose, which is half B. And so you're done. Okay. Is this all right?
Yes, sir.
Okay. So that's it. So you add up these two and you'll get B. All right. Okay. So let me move on to the next one. Fine. Is this all right?
Yes, sir. Yes.
Yes, sir.
Okay. Okay. So yeah, the next one is just computing a second derivative. It just is testing whether you understand what the second derivative is, that it's a symmetric bilinear form, the second derivative. So here you're taking a quadratic form. And if you differentiate it twice, you'll get twice the quadratic form, twice the bilinear form. Okay, so it's basically, this is the multivariable analog of if you differentiate x squared twice, you get 2. It's just the higher dimensional analog of that. So yeah, okay, so we just have to understand this. So, all right, so let's be quick. So let's compute the first derivative. So f of x plus h, this is a of x plus h. So this is Yeah, okay. So this is A of XX plus twice, by symmetry, A of XH is the same as A of HX. So this is twice A of XH plus A of HH, right? Okay. So this is your fx plus linear term. This second term is linear in H, plus E of H, and E of H, that's, well, f is scalar, so this mod of E of H, this is mod of A of HH, and this, by definition of the norm on multilinear functions, this is less than or equal to norm A into norm H squared, right? So this is little o of norm H. Okay. So that implies that f is differentiable and df at x applied to h is twice a of xh. Okay. Fine.
Yes, sir.
Okay. Now df is what? It's a map from Rn to the dual of Rn, linear maps from Rn to R. X goes to df at x. So for twice differentiability, we have to show this map is differentiable. So we have to look at the derivative of this map, right? And so what is the derivative of this map? So we look at df at x plus h minus df at x, right? And then we apply this to a vector. So these are both linear maps from Rn to R, right? So this whole thing belongs to L Rn R, right? And then we apply this to a vector k. Yes?
Yes, sir.
Okay. So what will this be? This will be, so df x plus h acting on k, this will be twice a of x plus h acting on k minus twice a of x acting on k. So a is bilinear, so the xk will cancel. You'll just get twice a acting on hk. Okay.
Yes, sir.
Yeah, so there is no error term here. This is already linear in H, right? So this is equal to a linear map, say L sub x of H acting on K, where L sub x is a linear map from Rn to L of Rn R. H goes to the linear map L sub x of H. So this is a linear map which sends k to twice a of hk. Okay. Yes.
Yes, sir.
So this is so linear function of H. So this implies that f is twice differentiable. That means df is differentiable. Yeah. Because df is differentiable and d squared f at x is equal to this linear map Lx. So this is an element of what? This is a linear map from Rn to L of Rnr. And this is identified with M2 of Rnr, right? Maybe I should write it as Rn cross Rn R, right? Bilinear maps from Rn cross Rn to R, right? And under this, the linear map, I mean, this linear map is H goes to the linear map, K goes to twice A of HK. This is identified with the bilinear map, HK goes to twice A of HK, right? Is that clear? And this is equal to the map twice A. So that's it. Okay.
Yes, sir.
Yes, sir.
Okay, good. So let's move on to the next one. We have 2 minutes left. Okay, fine. All right. The fourth one is quite easy. So okay, so first of all, you know that fx tends to plus infinity as x tends to infinity. So you just take any ball, let's say a ball of radius 1. So you let m be the infimum over x in the closed ball around the origin of radius 1 of f of x. Okay. Okay, there's less than a minute. Let me stop and start again. Okay. So I'll stop this and we'll start with this, the link to the second session. Okay. We'll use the link to the second session. Okay, so we're talking about problem 4. F is a C2 function on Rn, whose second derivative is strictly positive, acting on v comma v, where if v is any non-zero vector and at any point x in Rn. And suppose that fx tends to infinity as norm x tends to infinity, then you have to show that f has a unique minimum x naught in Rn. Okay. So the first thing is to show that f has a minimum, right? So for that, what you can do is you actually, so you don't need to do this. You just So there exists an R greater than 0 such that fx then is greater than equal to f of 0 for all x such that norm x is greater than or equal to R, right? Because fx tends to plus infinity as x tends to infinity. All right. So then you let x naught belong to the ball, closed ball of radius R around the origin, this same R, such that f of x naught is the minimum over this ball of f of x. Okay, so you take the closed ball and look at where f attains its minimum in the closed ball, right? So then actually that will be the global minimum, right? Because look, here's the origin, here's your x naught. This is the ball of radius R. So the value of f at x naught is less than or equal to all the values inside this ball. And if I go outside the ball, then fx is bigger than f0, which is bigger than f of x naught, right? Therefore, f of x naught is less than fx for all x, okay? Is this clear?
Yes, sir.
Okay, so if norm x is greater than or equal to R, then f of x is greater than or equal to f of 0, which is greater than or equal to f of x naught. Right? Thus, f of x naught less than or equal to fx for all x in Rn. Is this clear?
Yes, sir.
Okay. So we found a minimum. Now, why is the minimum unique? That is the main point, right? So suppose x1 in Rn is such that f of x1 less than or equal to fx for all x in Rn, right? So then naturally f of x naught has to equal f of x1, right? Yes?
Yes, sir.
Okay. Because both are less than or equal to each other. So then what can you do? So I have some other point x1, right? So maybe x1 is here. So what can we do then? What can we do? I'm giving you a hint. If you look at the screen, I'm giving you a hint. What can we do?
Something like mean value property.
No, just look at what I'm doing with the cursor. What can we do? What can we do? We have 2 points in Rn, so our function basically we want to say is a strictly convex function, right? Its Hessian is everywhere positive definite. So convex means what? Convex restricted to straight lines, right? So what should we do if we have these 2 points?
Yeah, you can consider the straight line joining them and
Thank you. Yes, join them by a straight line. That's what I've been doing all this time. Yes. So you
and in
let
between certain point you will get a point where the Hessian would be non-negative, non-positive then.
No, why is that? You can't just say
Because
that.
you,
Why is that? Why is that? So let's just draw the line first. So this is 1 minus t x naught plus t x1. Okay. Fine. Okay. So gamma prime t, this is equal to x1 minus x naught for all t, and gamma double prime t is what? What is gamma double prime t?
0.
0. Okay. Anyway, so this is a straight, since this is a straight, we don't need gamma double prime t actually. So since gamma is a straight line, d squared f at gamma t acting on gamma prime t, what is this? What is this?
Is d2f at gamma t acting on x1 minus x0. Oh,
Yeah, no, but in terms of curves, what is this? So it's the second derivative, right? Hessian, it's the second derivative along geodesics. So in Rn, it's just the second derivative along straight line, right? This we've proved right at the beginning. So this is d squared dt squared of f composed with gamma, right? Yes?
yes, yes.
Okay. So thus, if we let phi of t is f of gamma of t, right? Then phi double prime t is equal to d squared f at gamma t acting on gamma prime t. Right? So suppose x1 is not equal to x0, then phi double prime, this is d squared f at gamma acting on x1 minus x0, and then this x1 minus x0, this is non-zero. So therefore, this is going to be strictly positive by hypothesis, right? Yes?
Yes, sir. Yes.
Yeah. And also, phi has minima at t is equal to 0 and t is equal to 1, right? Because x0, x1 are minima of f, right?
Yes, sir.
So that implies that phi prime 0 is equal to 0, which is equal to phi prime 1. That's a contradiction because phi double prime t is strictly positive for all t, and so phi prime 1 has to be strictly bigger than phi prime 0. Okay, so that finishes it. Done? All right.
Yes, sir.
Okay. Okay, let's move on to the next one. Is this all right for everyone?
Yes, sir.
Okay. So, okay, let's take, so we have a smooth manifold, we have a complete vector field, and phi t is the flow, and omega is a k form. This is easy. We have to show Lx omega is lambda omega for some constant lambda, if and only if phi t star omega is e to the t lambda omega, right? Okay, so here we have to show phi t star omega equal to e to the t lambda omega for all t, if and only if Lx omega equal to lambda omega. So I've written it in the opposite order, but anyway, that's okay. So suppose the forward implication is easy, right? So if phi t star omega is equal to e to the t lambda omega for all t, then Lx omega, this is ddt at t equal to 0 of phi t star omega, which is ddt at t equal to 0 of e to the t lambda omega, and that is just lambda omega. Is this all right?
Yes, sir.
Okay. So we have to prove the converse, right? So suppose Lx omega is lambda omega. Okay. So then what can we do? So let's look at ddt of phi t star omega, right? So this is dds at s equal to 0 of, so we've done this kind of calculation before, right? Phi t plus s star of omega. So because this is a flow, I can write phi t plus s as phi s composed with phi t. And then I have star of this omega. And then pullback is contravariant. So I'll get phi t star on the left-hand side. Acting on phi s star of omega. And now phi t star is a linear map, so it will commute with the derivative. So this will become phi t star of dds at s equal to 0 of phi s star omega. So this is the Lie derivative. So this is phi t star of Lx omega. Lx omega is lambda omega. So this is phi t star of lambda omega. So this is lambda phi t star of omega. So you get what looks like a linear first order ODE, right? For this quantity, phi t star of omega, this is lambda times phi t star of omega. So how can you solve this? By the usual trick, right? You multiply by e to the minus lambda t, right? So e to the minus lambda t into ddt of phi t star omega minus lambda phi t star omega. This is 0. On the other hand, this is equal to ddt of e to the minus lambda t phi t star omega. Right?
Yes, sir.
So that then you're done, right? So this derivative is 0. That implies that e to the minus lambda t phi t star omega, this is constant in t. And so it's equal to the value when t is equal to 0. So when t is equal to 0, this is e to the minus lambda 0 into phi 0 star of omega. Phi 0 is the identity. E to the minus lambda 0 is 1. So this is omega. So that's it. So then you take the e to the minus lambda t to the other side and you're done. Okay? All right?
Yes, sir.
Okay, done. All right. Okay, so let's move on to the next one. Okay. The next one is slightly, there's a little work to do here. So if you have a closed manifold, that means compact Riemannian manifold without boundary, and f is a smooth function on M, such that all integral curves of the gradient flow vector field are geodesics, then you have to show f is constant. Right? So why is that? So you have your vector field x is grad f. And let's say phi t is the flow of x. So what do you know that if any integral curve is a geodesic, right? So let's say gamma so let P be a point in M. And let gamma T be phi T of P. The integral curve through P. Yeah. So we're on this closed manifold, right? So it could look like this. I have my my integral curve. So the integral curve is since it's for the gradient vector field. Well, since we're on a compact manifold, it has to accumulate somewhere, right? By compactness, it has to accumulate somewhere, right? So say it accumulates here. It keeps coming back to this place. Of course, it can't intersect itself, but anyway. So suppose it accumulates like this. Okay, so let say Q in M, and so let me write it like this. By compactness of M, there exists Q in M and a sequence Tn increasing to plus infinity such that gamma Tn tends to q as n tends to infinity, right? Okay. So what's the first point? The claim is that the limit x of q, which is grad f at q, this has to be 0. So the vector field has to vanish at any accumulation point. Okay? This is a property of gradient vector fields. Okay, so this I mentioned in class earlier, right? Yeah. So in fact, you can show that the integral curve actually has to converge to a 0 of the gradient vector field. Okay. So how do we prove this?
That is a non-trivial theorem though, right? That every
Yeah, that is a bit non-trivial. Yeah. So this is not so hard to prove that any limit point is a 0. So let's prove this. Okay. So we prove by contradiction. So suppose grad f at q is non-zero. Okay. So then you choose so let epsilon be half norm of grad f at q. Okay. So by continuity, can choose delta positive such that norm grad f at x is greater than or equal to epsilon for all x in the closed ball of radius 2 delta around q, right? This I can do, yeah? Okay. So what I'm going to do now is look at my point q. And look at the balls of radius delta and 2 delta. Okay. Then the point is, anytime I enter the ball of radius delta, right? Let m be such that norm grad f x is also less than n for all x in this ball. Okay. So the point is, anytime I enter this ball, I will have to spend a definite amount of time inside the ball. Okay. So suppose for some, say, tau in R, gamma of tau belongs to the ball of radius say delta around q. Okay. So then what is the, so note what is the speed of gamma? So mod gamma prime t. This is, since it's a gradient vector field, right? Gamma prime t is just grad f at gamma t. Okay, so actually let me take this m to be the maximum of norm grad f on the whole manifold. Oh, I shouldn't use m here. Okay, let me use c. Okay, fine. So let me use c here. Sorry. Yeah. So then this thing, the speed of the integral curve, this is less than c, right? So for s greater than or equal to 0, sorry, this should be this should be tau here. So the distance between gamma tau and gamma tau plus s, this is less than or equal to the integral from tau to tau plus s of norm gamma prime t dt, right? So that's less than c times s. So this is less than delta if s is less than delta over c. Right? Yes, so that means that gamma of tau to tau plus delta over c, this will be contained inside the closed ball of radius 2 delta around q, right? Yes? By triangle inequality.
Yes, sir.
Plus 2 delta. Okay. So what does that mean? Now look at the function f along gamma. So what is ddt of f of gamma t? So this is df gamma t acting on gamma prime t. So this by definition of the gradient vector field is grad f at gamma t acting on gamma prime inner product with gamma prime t. And this is, since gamma prime t is also grad f, this is just norm grad f gamma t whole squared, right? And norm grad f inside this ball of radius 2 delta, this is bigger than epsilon. So this derivative is bigger than epsilon squared for all t in the interval tau to tau plus delta over c, right? Okay, so that implies that f of tau plus, sorry, f of gamma of tau plus, so f of gamma t actually, this is greater than or equal to f of gamma tau plus epsilon squared into delta over c for all t bigger than tau plus delta over c. right? So you increase by a definite amount. Each time you enter the ball, when you exit, you increase by a definite amount. This proof is getting a bit long. It's a bit longer than I thought, but the idea is not difficult. The idea is very simple. Each time, look, each time I enter the ball, this is say gamma of tau, right? Then I have to stay inside the ball for a certain amount because my maximum speed is bounded. Now, if I stay inside the ball for a definite time, then my f has to increase by a definite amount, okay? Because the norm of the gradient vector field is bounded below. And the derivative of f is the norm squared of the gradient vector field, okay? So I have to increase by a certain amount. So if I enter this ball infinitely often, right, then each time I enter the ball, I'm going to increase by this amount, right? Epsilon squared into delta by c. Is it clear?
Yes, sir.
Okay. So that will tell me that f tends to plus infinity along this integral curve. That's a contradiction because f is bounded. That's it. Okay. So if we choose a subsequence of Tn such that Tn plus 1 is greater than or equal to Tn plus this delta by C for all n, then by the above, so we choose a subsequence so that f Tn plus 1 is bigger than Tn plus, and we choose it the Tn so that f of such that gamma of Tn belongs to the ball of radius delta around Q for all n. Okay, so then f of gamma Tn plus 1 greater than or equal to f of gamma Tn plus epsilon squared delta by C, right? And so you apply this n times, that implies that f of, this is true for all n. So f of gamma Tn is greater than f of gamma T0 plus n times epsilon squared into delta by C, and this tends to plus infinity as n tends to infinity. Is this clear? Yes? That's a contradiction. So that proves it, all right? Okay. All right. So this proves the claim. So thus, gamma Tn converges to Q such that grad f at Q is 0. Okay. So up to now, we still haven't used the fact that gamma is a geodesic, right? So let's do that now. How can we use that? So then the speed of, so since gamma is a geodesic, right? This implies that norm gamma prime is constant. Yes? Geodesics have constant speed, right?
Yes, yes.
But norm of gamma prime t, what is this? This is the gradient vector field. This is norm of grad f of gamma t. So if I look at Tn, my sequence of times Tn, right? Along this sequence of times, this converges to norm of grad f at Q, which is 0, right? So that implies that norm gamma prime T, this is 0 for all T because it's constant, right? Yeah.
Yeah.
So that implies that gamma prime 0, what is this? This is grad f of gamma 0, which was P. This is 0. Right? And this is true for all P in M. P was arbitrary. So that implies that grad f is identically 0. And so f is constant. Okay. Is this all right? P was arbitrary, right? I started with any P. Okay. Is this clear? Yes?
Yes.
Yes,
Um,
sir, yes.
Okay. All right. So let's stop this session and start a new one. Okay.
There might be a simpler way to do this problem. Can I say it?
1 second. Yeah, sorry. You say it quickly. Yeah, say it.
Yeah, so if let's say if gamma is an integral curve of the gradient vector field,
Yeah.
then I get the ddt of f of gamma t is df
Correct.
of gamma
Is-
prime t, and that
yeah,
that
that's
is the
increasing. Norm gamma, norm of grad f of gamma t squared. Yeah, right.
yeah. So and then so that derivative is grad f square, and then
Yeah.
I look at I differentiate grad f square along the integral curve. That will be 0 because gamma is a geodesic.
No, wait. You differentiate grad f squared.
Yeah. So gamma prime
I see.
inner product
Oh,
of
okay.
grad f gamma grad f.
1 second. So what you're saying is, so this first thing is all right. ddt of f of gamma t, this is
So you have to share the screen.
oh, sorry, I forgot. Sorry. 1 second. Yeah. So right. So ddt of f of gamma t, this is let me write it as inner product. So inner product grad f gamma t, grad f gamma t, and then you take the second derivative of this.
Yeah.
Oh, okay. Yeah, actually that's, oh, sorry, I didn't see this. Yeah, this seems much quicker. Yeah. Thank you. Yeah, the other one, if you know the fact that any limit point is a critical point, then it's easy. But if you have to prove that, it's a bit long. So, okay, yeah, if you do this, this should work. So this will be twice, yeah, you're right. Twice inner product, nabla sub, so gamma prime. So I'll just write that. Nabla sub gamma prime of grad f, right? And nabla sub gamma prime of grad f, grad f is again gamma prime. So this is nabla sub gamma prime of gamma prime, grad f. And this is 0 because gamma is a geodesic. That's what you're saying, right?
Yeah.
So that means the second derivative is 0. So therefore, it's a linear function, right? So that implies that
The
f
first
of,
derivative should be 0 because
well, let's see.
otherwise,
So, well, let's just do it. So f of gamma t is therefore f of gamma 0 plus t times the first derivative. So the first derivative is norm of grad f at gamma 0, right? Whole squared. That's it. Yeah. So
yes,
this tends to plus infinity unless this is 0. So therefore this is 0. Yeah. Okay, very good. So this so you can just say this is bounded in T because f is bounded. So that implies that norm grad f at gamma 0, this is 0. So you're done. Okay, very good. Thank you. This is nice. Yeah. Okay. Is this all right?
Yes, sir.
Okay, good. Okay, so 7 is quite straightforward. Okay, let's just do that quickly. So 7, you have Riemannian normal coordinates, right? So what are y1 to yn? Normal coordinates, y1 to yn. These are of the form some linear isometry T composed with x of whatever, x naught. So is it P? No, the normal coordinates near P, yeah. So xp inverse, yeah. Right, so this goes from a ball around P to Rn, right? And T is a linear isometry from the tangent space TPM to Rn. Right. So now if I look at, so let me call this y, which is y1 to yn. So dy at P, this is by the chain rule, it's going to be T composed with the derivative of xp inverse at P. And this derivative is the identity we already know. So the derivative is just T, right? And dy at P acting on del y at P, del yi at P. This is equal to EI. Okay, so this says that so dyp is a isometry. And it maps del yi at P to EI for all I. That implies that del yi, these are an orthonormal basis at P. Right, this is an orthonormal basis of TPM. So now dy1 at P up to dyn at P is the dual basis. But since del yi at P is an orthonormal basis, dual basis is given by taking inner product, right? So that means dyi at P acting on V is equal to inner product del yi at P acting on V. Is this clear? Right?
Yes, sir.
Okay. So this is for all V in TPM. For all I. So for all V in TPM, if I look at the inner product of grad f at P with a vector V, then by definition, this is dfp acting on V. But now yi's are a coordinate system. So I know what the derivative is in terms of the coordinate system. This is sum over I del f del yi at P into dyi at P acting on V. But this dyi acting on V is the inner product. So this is sum over I del f del yi at P into inner product del yi at P with V. And then I can take the inner product outside. So this becomes inner product of sum over I del f del yi at P into del yi at P, inner product with V. Okay, so this is true for all V. That implies that this grad f at P must be equal to this, right? Is this clear?
Yes, sir.
That's it. So that proves the first part. And the second part we've already done, right, in class? Yes? Yeah, do you remember how to show the second part, right?
Yes, sir.
Yeah, see, the point is the curve see, I mean, the geodesic. So, okay, let me write it like this. So let say Vi be del yi at P. So then, so let gamma I of T be the geodesic with initial condition Vi. So xp of T Vi. This is a geodesic. Yeah. So then what is Y of gamma I of T? So this is dyi composed at P composed with xp inverse of xp of tvi. So this is t dyi at P of vi, and vi is del yi at P. So this is just TEI. So these geodesics map to straight lines, right? In the direction EI. Yes? Yes?
Yes, sir. Yes, sir.
So thus, the Hessian of f at p acting on vi comma vi. This is, as we've shown before, this is d squared dt squared at t equal to 0 of f of gamma I of t, right? Yes.
sir.
And this is going to be del squared del yi squared f at p. Since gamma I maps to the straight line in the direction of ei, right? Yes.
Yes, sir.
Yeah. I mean, I'm just differentiating f twice along this straight line in Rn, right? If I look at f composed with y inverse, right? So then I'm just differentiating along a straight line. That's the second partial with respect to yi, right? And that's it. So
Yes,
then
sir.
the vi's are an orthonormal basis. The Laplacian is the sum over I. And so you get the formula that you want. Okay? I'm not writing more. All right.
Yes, sir.
Okay, fine. So that gives 7. Now 8. Yeah, 8. So part A we've already done in the notes, right? I'm not doing this again. This product formula we've done in class, we've done in the notes. Yes? I'll just do part B. All right.
Yes, sir.
Yes.
Okay. So part B. So the idea is you put x to be grad phi. Okay. So then divergence of phi x this is inner product grad phi x plus phi divergence of x. So what does this become? This becomes x is grad phi. The first term becomes norm grad phi squared plus phi divergence of grad phi is Laplacian phi. So this becomes phi Laplacian phi, right? So now yeah. So now so let psi equal to phi plus a constant m. No, m is the manifold. So phi plus a constant c, where c in R is such that psi is greater than or equal to 0 on m. Right? This I can do. Yeah, because phi is bounded below, m is compact. Yes?
Yes, sir.
Okay. So then Laplacian psi is equal to Laplacian phi, which is given to be greater than or equal to 0, and psi is greater than or equal to 0. So the integral of psi, Laplacian psi, dvol over m, this is greater than or equal to 0. But this integral, psi Laplacian psi, dvol if I use this formula here, this is equal to the integral over m of divergence of psi grad psi minus norm of grad psi squared, right? Yes?
Yes, sir.
I'm applying this formula with phi replaced by psi, that's all. Yeah. And now the first term is a divergence that vanishes by the divergence theorem. So then this just becomes minus integral of grad psi squared, norm grad psi squared, right? So this thing is greater than or equal to 0. That implies that integral of norm grad psi squared devol, this is less than or equal to 0. That implies that this is 0. So norm grad psi is identically 0. And that implies that psi is constant. And that implies that phi is constant. Okay. All right.
Yes, sir.
Okay. So that's it. Okay. So 9 and 10 are just from the class, right? And the notes. So we don't have to do that. 11 we've also done in class. 12 we've also done in class, right? Yeah.
Yes, yes.
Okay, so 9, 10, 11, 12 we've all done in class. It's just 13 is left, right? Okay, so yeah, so 13, in fact, I did this at the end of the last class, but most people had left. So let me just say a word about this. So 13, you have to prove this formula. That is, so if M and N and you have UT from M to N, suppose this is a geodesic homotopy, right? Then in the last class, we proved this formula for the second derivative of the energy, d squared dt squared of energy of ut. This is the integral over m of the norm of grad of del u t del t whole squared minus the sum over I in our product, basically a curvature term, Rn of dut ei del ut del t acting on dut ei del ut del t. Okay, then the whole thing integral devol. All right, we proved this in the last class. So have a look. This is in the notes also. Okay. All right. So this is greater than or equal to 0 if the sectional curvature of n is less than or equal to 0, because then these curvature terms are negative or non-positive. So there's a minus sign here. So that will give you something non-negative. All right. Is this clear? Hello. Can you hear me?
Yeah, it is clear.
Okay, so this is done in the notes. I've done it in the class also. It's in the class notebook notes. You can have a look from wherever you like. Okay. So we've done this. Okay? I'll just show you here. It's here. This yeah, this formula here. Okay. Okay, so here's the proof. You can have a look. Okay, so there's this. So that shows that that gives you the first part of the problem. Okay, you're assuming sectional curvature of n is non-positive. Okay, so that you get the energy is a convex function along the geodesic homotopy. Now suppose that F0 has minimum energy in its homotopy class. Then you have to show if F1 is harmonic, then the energy is actually constant. So see, if F0 has minimum energy, F0 is harmonic. And then if F1 is harmonic, what you're saying is that all of the maps have the same energy and they're all harmonic. Okay. So when you move by a geodesic homotopy in non-positive curvature, if you start with a harmonic map and end with a harmonic map in the geodesic homotopy, that is, if you take a geodesic homotopy between two harmonic maps, then all the maps in between are going to be harmonic maps, okay, with the same energy. That's what we're proving. So that second part is just a little bit of calculus. So F0 has minimum energy in homotopy class. So let phi of t be the energy of ft. Okay, so then phi has a minimum. So okay, maybe I should say it this way. So then, so since F0 has minimum energy in its homotopy class, that implies that F0 is harmonic, right? So then, so tau F0 is identically 0, right? So then phi prime t, this is, we know, minus integral over m of inner product del ft del t with tau of ft dt, dvol, sorry. So this is equal to 0 at t is equal to 0 and t is equal to 1, right? Yes, because F0 and F1 are harmonic. Yes? Yes?
Yes.
Yes, sir. Yes, sir.
And phi double prime is greater than or equal to 0 by part A, right? So phi prime is monotone. And phi prime 0 is equal to phi prime 1 is equal to whatever, is equal to 0. Yeah. So since phi prime is monotone and it takes the same value at 0 and 1, that implies that phi prime is constant, right?
Yes, sir.
Yeah. If a monotone function takes the same value at 2 points, then it's constant in the interval between those 2 points, right? Yes?
Yes, sir. Yes.
So phi prime is identically 0 because at 0 and 1 it takes the value 0. And so therefore that implies that phi is constant. And that constant is phi 0, right? Which is energy of F0. Okay, so that proves that all the maps Ft have the same energy as F0. Okay. And so energy of Ft is equal to energy of F0, and this is equal to the minimum over U in the homotopy class. So, okay, maybe I should write it like this. So U homotopic to F0, U is C2. Actually, well, yeah, C2 is fine. Yeah. So energy of U. But the point is the homotopy class of F0 is the same as the homotopy class of Ft, right? Because F0 and Ft are obviously homotopic, right? So this is the minimum over the homotopy class of Ft, right? Yes?
Yes, sir.
But that implies that Ft is harmonic, right? Because it has minimum energy in it in its homotopy class. Okay, so that's it. So all the maps Ft are harmonic. Okay. All right.
Yes, sir.
Okay, so fine. We have about 8 minutes left. Now you can ask whatever questions you want or comments. Yeah. So, oh, there was one more question that may come up later. So, yeah, there's one simple question that if okay, so maybe I'll call this 14. This, I forgot to add this in the notes. So suppose omega is a closed form. So d omega is 0. Omega is a K form. So then you have to show that if sigma is a K chain, which is closed, so boundary sigma is 0. Okay. So then you have to show that the integral over phi t composed with sigma of omega is 0 for all vector fields x in chi m. Sorry, not 0. This integral is constant. So it's constant. Okay, so maybe I should write it properly. So I have x is in chi n with flow phi t. Okay. So yeah, then you have to show that this is a constant. This integral over phi t composed with sigma. Okay, so phi t composed with sigma is a bit misleading. What this means is that if so this is defined to be summation ai phi t composed with ci. If sigma is summation ai ci. Okay. All right. This is just
Yes,
a
sir.
shorthand notation for this. Okay. So how do you show this is constant? So this integral, first of all, you can write this as the integral. So you differentiate this. So ddt of this integral, this is this integral is the same as the integral of phi t star omega over sigma, sorry, of phi t star omega. So this is the integral over sigma by differentiation under the integral sign of ddt of phi t star omega. So ddt of phi t star omega, we know what it is. It is phi t star of Lx omega. And what is Lx omega? This is by Cartan's formula, d of Ix omega plus Ix of d omega, but d omega is 0. So this is d of Ix omega, right? So this becomes integral over sigma phi t star of d of Ix omega. But now d, by naturality of d, it commutes with pullback. So this is integral over sigma of d of phi t star of Ix omega. But now by Stokes, this is equal to the integral over boundary sigma of phi t star of Ix omega. And boundary sigma is 0, so this is 0. So that's it. So this derivative is constant, is 0, so therefore the function is constant. Okay?
Yes, sir.
Yeah, this is another small exercise here. Okay, that's it. Yeah. All right, so there are about 3 minutes left. Any questions? Quick questions?
Sir, is there any possibility that we maybe ask the long derivations in the exam?
I don't remember. Yeah, not very long. Yeah, not very long. Yeah. Anyway,
No,
there
no,
are not.
I am asking about that harmonic map seed flow, the existence of long-term solution or short-term solutions.
No, nothing that long. No.
Oh,
Whatever you'll be asked is from the assignments. So whatever is on the assignment, that's all. Yeah.
oh, okay.
Yeah, whatever is on the assignment. So yeah, I don't think there's anything outside the assignment. So yeah.
Okay.
Yeah. So if you understand the assignment well and you can work it out yourself, then you should be fine. Yeah.
Okay,
Okay.
sir. Thank you.
Yeah, it's all from the assignment. Yeah. It's all from the assignment. Okay.
Sir, question number 11 that follows directly from Eel-Sampson, right?
Well, and the other problem, right? That not just Eel-Sampson, but also the theorem. You have to state what theorems, right? So the theorem that if the Ricci curvature is positive, is non-negative, and if it is positive at some point, and if the sectional curvature of n is non-positive, then the map is constant, right?
Okay, fine.
So all of that, yeah. So you have to say, yeah. So
Okay.
yeah. So you have to say sectional curvature of the spheres are positive, hence Ricci curvature of the sphere is positive, and sectional curvature of the target manifold non-positive implies that any harmonic map is constant, and so yeah. So yeah, you have to quote whatever theorems you're using, you have to quote that, right? So
Yeah, okay.
yeah, you can't just say, yeah, no, you have to quote whatever theorems you're using. Yeah, so if you use any theorems, state them clearly, okay? So yeah. Okay, then. So good luck. I guess this is it. And yeah, well, thank you for listening. And so yeah, okay. All right.
Thank
Thank you, sir.
Thank you, sir. Yeah.
Okay. Bye bye.